All right, I think I'm in business. Hi, everybody. So this is the worksheet problem that I gave you in the context of expansion work. If you haven't tried the worksheet problem, you should hit pause at this point. It'll be really helpful if you go through and give all of these problems a good faith effort. And after you do, come back, check in, and see if this helps. All right. So here's the problem statement. Sample of 4.5 grams of methane occupies 12.7 cubic decimeters at some temperature. Does this gas do more work if it expands isothermally against a constant external pressure, 339 torr, until the volume has increased by some amount, or if the same expansion occurs reversibly? First question I ask you is, why is this first process not reversible? So you may notice that it doesn't explicitly say that in the problem statement. It doesn't say that this isn't reversible. But if the counter example is a reversible process, then we can sort of reasonably infer that the first process is not reversible. How might you know that? I'm not going to work all the way through the calculations, but you should have recovered something that looked like this. If you calculate the pressure of the gas, you'll find that it's 0.56 atm. If you calculate the external pressure, you'll find that it's 0.45 atm. And here's the point. These are not balanced. Right? If I have a gas at 0.6 atm and a surrounding atmosphere at 0.4 atm, it is just going to automatically expand without doing anything. I can't stop it, and there's nothing that I can do to reverse it with an infinitely small change in the opposite direction. Right? Therefore, this first process is not reversible. Second question, calculate the work done by both processes and illustrate your answer graphically. Again, I'm not going to work all the way through this. Here are the numbers that I get. Negative 149 joules for the first one and negative 167 for the second. Here's the important note here. These are negative. And a negative work or a negative heat means that the system lost energy. Right? It expanded and did work. So this is usually called an acquisitive convention, and this is really important when you're doing calcs. So we're going to get more and more complex, and you want to make sure that you get your pluses and minuses right, or it's going to cause some problems. The second part of this question asks you to illustrate your answer graphically, and here's how you can think about that. So let me switch my lovely pointer. And here's our formula for PV work, minus P external dV. You'll note that this is an integral, right? In integrals, we associate with areas under curves. So what this sort of suggests we should plot is a PV plot. We've seen these before. And the work is associated then with the area under the curve associated with the gas expansion. So here you go. In the first process, we were at 339 torr. If I remember right, that was like 0.45 atm. My cursor is not being cooperative. So process one, we start here. We expand against a constant external pressure. This delta V was something like 3.3 cubic decimeters. Right? And then the work is this area under the curve. That's the work. In the second process, the gas starts at higher pressure. I think it was something like 0.6 atm. And it undergoes an isothermal expansion. Somehow my cursor's not being. Remember that the isothermal expansions are the hyperbolous. So this one here is the isothermal reversible expansion. And the work associated with that one is the area under that curve. The second one has more area under the curve, so I would expect to get more work. And that's exactly what you get in these formulas. Is the change in internal energy, what is the change in internal energy for both processes? Think, think, think. Here's the answer. Delta U is 0 for both. Remember that U is a state variable. So if they start at the same point and end at the same point, then the change in energy has to be the same. Furthermore, because both processes are isothermal, delta T is 0. Recall that U only depends on temperature, right? For an ideal gas, that's the only variable that matters. And if that's true, then delta U must be 0. Right? So the change in internal energy for both of these processes is 0. Last but not least, does the system absorb heat in the second process, the reversible isothermal expansion? Why doesn't the temperature rise? Here's the answer. And this is maybe the key to the whole thing. If you understand this, then you get the first law of thermodynamics. The answer is yes. The isothermal reversible process absorbs heat. Well, if that's true, why doesn't the temperature rise? And the answer is the first law of thermodynamics. The first law of thermodynamics tells me that I can exchange between work, heat, and energy. And specifically, I could imagine a process in which all of the absorbed heat is converted automatically to work with 100% efficiency. And that's exactly what happens, right? In an isothermal reversible process, all of the heat that it absorbs is converted to work and the temperature doesn't go up. All right, I will stop here and I will see you next time for some heat transactions.